the squeeze theorem is a very powerful theorem, and it's used quite a bit in different areas of mathematics, and you'll see it pop up from time to time throughout the entire calculus series here, Calc 1, 2, 3, and beyond. So let's introduce the idea now and apply it to a couple of relatively simplistic examples, and we'll use this a little bit later on for things that are a little bit more difficult. So if h of x is less than or equal to f of x, which is less than or equal to g of x for all x, in an open interval containing c, except possibly at c. So this is true except for possibly what's going on at c. And if the limit as x approaches h of x is L, and the limit as x approaches c of g of x is also L, so the limit of h of x as we approach c and the limit of g of x as we approach c are both equal to L, then the limit as x approaches c of f of x is also L. This guy in the middle is L. What's happening is the squeeze theorem, we're squeezing it in. Let's draw a picture here and kind of see what's going on. Basically, the idea is the way you use this. You want to find the limit as x approaches c of some function f of x, and you're not sure what it is. But you can find h of x and g of x such that this statement is true. So suppose we have, let's just say that this is h of x. Let's just put c right here. And h of x is less than or equal to f of x, which is less than or equal to g of x for all x in an open interval containing c except possibly at c. So the limit as x approaches h of x of c goes to L, so it goes to L. And now I have g of x. I'm going to jump to g of x. I know that g of x is greater than or equal to h of x everywhere, but as I approach c, that limit also goes to L, so g of x must do this. Something like that. And then I have f of x, which is in between. So f of x is in between everywhere, so it gets forced in here like that. So what this theorem is actually saying is that because the limit of h of x as x approaches c of h of x and g of x is both L, and f of x is forced in between everywhere, then the limit as x approaches c of f of x must also be L. That's kind of graphically the explanation of what that means. Now, prove that the limit as sine x over x as x goes to infinity is 0. Well, right away, this is kind of weird because if I break this up, let's just break this up like we normally would. If I take a look at the limit as x approaches infinity of sine of x, that doesn't exist because sine of x goes like this forever, right? It doesn't approach anything. And as x goes to infinity of x, so if I take a look at the limit as x approaches infinity of simply x, well, that goes to infinity, which also means the limit does not exist. So what I have is something that doesn't exist divided by something that doesn't exist, which has got to seem odd. So how are we going to get from there to 0? Well, let's take a look at this. I know that sine x has a minimum of -1 and a maximum of +1. So sine x is always greater than or equal to -1 and always less than or equal to +1. Okay, that would then imply that a -1 over x must be less than or equal to sine x over x, which is less than or equal to 1 over x. I need to specify here for x greater than 0, for x positive. For x positive, this is true. So what I can do is I can take the limit as x goes to infinity of -1 over x. That then has to be less than or equal to the limit as x goes to infinity of sine x over x, which must be less than or equal to the limit as x goes to infinity of 1 over x. See, this here in the middle, this is this f of x that I'm trying to figure out what the limit is. Well, on the left-hand side here, this limit is clearly 0. Because as x goes to infinity, I have negative 1 over something huge. That's approaching 0. So 0 is less than or equal to, I don't know what this limit is. This is what I'm trying to figure out. The limit as x approaches infinity of sine x over x, which is less than or equal to, well, again, as x goes to infinity, 1 over x, I get 1 over something huge. That approaches 0. So see what I just did? I just took the limit as x approaches infinity of sine x over x, the piece that I'm looking for, and I squeezed it in between these two other limits that are equal to each other. See, if this limit was 0 and this limit was 2, that wouldn't help me. All that would tell me is the limit is somewhere between 0 and 2, but it doesn't tell me what the limit is. But because this is 0 and this is 0, these guys are equal to each other, then this limit right here must also be 0.